So first we want to take a look at the relationship of the Virtuoso design environment to the open access database. Here's a diagram showing that the standard API is actually the standard program interface that we call open access. Underneath that is a data model and also a reference database. So Cadence provides the standard API interface through skill, and then the data model and reference database underneath that, which store and represent the data. The types of data are shown in the blue circle here that typically are stored there. There's other types, but typically would be things like floor planning, schematics, and layout. Now you can see too the interfaces are listed above as far as the Cadence EDA tools is one set of interfaces into this environment. Other EDA industry tools which use the open access database, tools from other companies like Mentor's Caliber verification tool, for example, and then university research. So different universities are going to be using this database to write tools and applications for various aspects of their research. So the purpose of the database was to provide a common database and API for next generation integration of digital and custom tool flows. So within the Cadence EDA tool flow, for example, the digital encounter based tools and the custom IC Virtuoso based tools share the same database. It's enhanced and maintained by the industry-run Open Access Coalition under SI2 as an open database for tool integration. So not just Cadence has input into this, but other customers and vendors who are part of this coalition have input as to what the database looks like and what the access functions do. And then finally, it's also a high capacity connectivity based database with structures to compactly handle large designs. So this is very important because as this was developed, the size of the data that was having to be handled as far as transistor count and area of design were increasing dramatically for the next generation nodes. Here's a diagram showing a database-centric flow. And this is important because on the outer rim you see the tools, the various tools. That can be Cadence tools, they can be other vendor tools, that can be research tools, but rather than historically where you would have to translate data through data formats such as GDS2 and LEF and DEF and a variety of formats that required translation from tool to tool to move data, here the tools write to the common open access database through the common API layer, and the data models representing the netlist, physical, electrical layout, and schematic information are common, so when one tool writes to it, another tool can read it. This is very important in allowing both groups within a company and groups between companies to work together efficiently in tool flows and in chip integration. Now when you write skill code to access the database, it's important to understand where to look up information about database access. And within the Virtuoso Design Environment Skill Reference Manual, there is a chapter on database access. So if you go to that manual and in the PDF, for example, search for database access, you should locate that section. The types of information there are related to data that's stored as objects, the database access functions that you need to access the database, the attribute retrieval and modification information. So once I have a database object, what attributes can I retrieve from that object and which one of those attributes can I modify? Now there are specific functions that you're going to be using and that we'll be using in this course, such as DB open Cellview by type. You can look that up in the online documentation. and also look at the table of contents to see what other commands you might be interested in. So in order to examine the data model, we will first of all look at what we will call a data model roadmap, or basically how to read the various parts of the data model entity relationship diagram. So in this case, you can see we have, first of all, an ellipse. An ellipse would represent a class of object types that share the same attributes. For example, shapes are one of those classes of objects. Next, we see a rectangle, and that would represent a specific object type. In this example here, we're showing a cell view. And then around the cell view are clustered the attribute names. So in the case of a cell view, we have the live name, cell name, and view name. Now this is not a comprehensive list, but these are common attributes that you would reference in your programs and database queries. Now the arrows are important in that they represent the relationship between two object types or two object classes. And then each arrow is labeled with an attribute name. So when you write your queries, you can look at this data model roadmap and devise your queries based on the names of the arrows and the names of the either ellipses or rectangles. So in this case, for example, if I had a shape, I could say shape tilde arrow cell view, and I would then locate the cell view that shape was stored in. Alternatively, I could say cell view tilde arrow shapes, and I would find all of the shapes within that cell view. Now the importance here of the arrow, whether it's single or double, determines whether you're going to get one or zero things or one to many. So in the case of a shape pointing at a cell view, a shape is located in only one cell view. But if I look at cell view tilde arrow shapes, it has a double-headed arrow, meaning I can get multiple shapes back. And that would also indicate to me when I was writing my queries that I would be getting a list of information back as opposed to a single item. Here is an overall view of what we're calling a data model snapshot. Now there is more detail in the manual that has a more extensive view of this particular one, but this is condensed to fit within the confines of this PowerPoint slide. So it was an attempt to show you the relationships between the various objects and classes of objects within the database. The outer blue box, you see it says cell view, and basically on the left, bottom, and right is the cell view. So the cell view contains or can contain these various types of objects. And you'll see that there's a, for the most part, a one-to-many relationship with these particular items. The classes are in the yellow ellipses in the middle. Those are groups of things that share the same attributes, and then you'll see the yellow arrows pointing to typically the things that are contained within that class or the specific database objects. So, as you view this would help you determine, what types of objects you could query, and then some of the attributes that are clustered around those. Now, in the newer IC6.1, the number of objects has been greatly expanded. For example, now there's markers, blockages, different types of boundaries, different types of vias. These are all new objects in the 6.1 environment that previously would have been stored either as, in the case of markers, as a layer with some, general information about it, but it would not have been a formal object. Also the same with a via. Previously, a via would have simply been an instance it would have been a master cell in a library that you would create an instance of when you placed it. Now it's actually defined formally in the TEC file and as a data object you can reference. So when we talk about opening cell views, previously we had opened them graphically. Okay, we would called GE Open, or we would go to the library manager and we would open up a Cellview graphically, and from there we would capture the Cellview data object that we could then reference information from. In this case, what we're going to explain is how to open it non-graphically, meaning no graphics window will pop up, but we'll still have access to the same data as we had before when we had the graphics there. So the function to do that is called dbopenCellviewByType, and when we call that particular function, we provide it things like the library name, cell name, view name, and then access mode. Also included is the view type. At a minimum, you need to give the library, cell, and view, and the view type and access mode are defaulted. The view type is defaulted based on the view name, and the access default mode is read. Notice that this is not keyword based, but positional parameter based, so you need to put them in the correct order. Here's an example of using it. In this case, we'll use it to create a new cell view. And the reason it's a new cell view is the last parameter you can see on the far right is a W. Okay, if we wanted to add to an existing cell view, we would use A for append. But the command here is dbopenCellviewByType. The library is master, the cell is new, and the view is layout. And then in this case, we're also specifying the view type and the mode, which is write. And what we'll do is, assuming it can access that library and create a cell in it, we'll open a cell view and return to you a database object. And then that CV variable you can now use in further functions, things like creating data. When you use a dbCreate, you would pass in the cell view for that. So one of the first data objects we want to look at is a shape. Now a shape is a class of objects. You can see here in the middle, shape is an ellipse. All of the shapes would have the common attributes of layer name, layer num, and LPP. LPP meaning layer purpose pair. And then underneath shape, you can see the different types of shapes that make up that class of shapes. Things like a polygon, a rect, and a line. Now you can see clustered around polygon is some unique attributes to polygon, which are endpoints and points. Those would be the actual coordinates that make up the polygon. And so a polygon then, as far as attributes, would have endpoints, points, as well as the common attributes of shape. So a polygon would also have layer name, layer num, and LPP. Rect and line are the other two listed there. So just looking at the shape and the types of shapes, the diagram shows us, their relationship. Now looking from a shape to a cell view, for example, we say shape tilde arrow cell view, and you can see we go up to the cell view object at the top. And then coming back, we could say cell view tilde arrow shapes and get a list of all the shapes. Now one important thing to look at here is the shapes are organized in two ways. One is just by the entire list of shapes in the cell view, but the other is to the right here. You'll see the branch called layer purpose pairs. And what that points to is essentially a categorization of the shapes by their layer purpose. Think of it kind of like a folder system. So each group of shapes that are on the same layer are in the same folder. Okay, the folder here is called an LP. That's the type. But to get to the list of layer purpose pairs, we would say Cellview tilde arrow layer purpose pairs. That can also be abbreviated as LPPS. So by looking at the layer purpose pairs in the cell view, we could search through that list of layer purpose pairs and find, for example, layer name equal to metal 1. Okay, and with that in mind, then once we have the layer name equal to metal 1, we could then locate all of the shapes on metal 1 by taking that object and saying tilde arrow shapes. So if you are going to be processing information by the layer they are on, it would be typically much faster to go and locate the layer purpose pair quote folder and then access all the shapes within that layer purpose pair. That way you don't have to sort through all the shapes to find just the ones on metal 1, for example. You can simply look in the database, which has already organized that for you, and take advantage of that. Here we'll examine how to create a shape. There are several skill functions that create database objects. The functions that we'll be looking at here begin with dbCreate. So if you looked in your skill finder and just typed dbCreate and clicked, starts with, you would find all of the functions that start with dbCreate. They would be things like dbCreate rect, dbCreate polygon, dbCreate path. So when we call the function, we need to pass it in a Cellview, because that's what we'll be creating the shape in, as a Cellview, and then enough other arguments to describe that object. Then it will create the object and return a new database object to us. So here's an example of using the dbCreateRect function to create a rectangle on a layer with a given bounding box. So here we have CV first equals db open Cellview by type. That's our non-graphical way of opening a Cellview. And we're going to pass in master new layout mask layout W. So we're basically creating a new layout Cellview. Next we're going to call dbCreateRect, Cellview, metal 1, and then the bounding box, which is a list of the lower left and upper right coordinates. And so dbCreateRect will, in that Cellview, create a rectangle on that layer at that location and then return to us, and we will store it in the new rect variable, that database object. Next, we want to look at a way that we can update shapes in the database. We can use the tilde arrow operator to update a shape. And in the table here, we have some example expressions that will show you what you can do with that particular shape in the database. So let's say we wanted to move a rectangle to a new location. In the first line here, we'd use tilde arrow bbox equals, and in the example we'd say a rectangle database object, tilde arrow bbox, access the bbox attribute, and assign to that a new bbox. So with that new bbox would be a list of coordinates that would provide the new location of the rectangle. The next example we see is changing the shape's layer. And we would use tilde arrow layer name equals. And in the example, we'd have a rectangle object accessing the layer name attribute with tilde arrow layer name. And to that layer name attribute, we would assign the value thinox. And this is a string. And it's important here too, when you do these assignments, that you check what type of data the database is expecting you to send. Whether it's a list in the case of the first one or a string in the case of the second one. Next, we'll look at how to change a path's points. So if we have a path that has a specific set of points to go from one location to another on the screen, we would then change that path's points with a tilde arrow points equals query. And so you can see in the example, we'd say a path tilde arrow points equals new points. And basically in this case, we're assigning 2 points, the new points for that path. And then in the last example, we would change the path's width. So the attribute to change the path's width is called width. And so in the example, we see a path tilde arrow width is assigned the value of 3.0. So again, if you were looking at that on the screen and it had a 1.0 width originally, and you changed it to 3, you would see the width of that path expand to 3.0. Now there are attributes you are not allowed to set. One example here would be on a path. There's an attribute called n points, and that's computed by the system anytime you change the points in the path. So n points is the number of points, and it's maintained by the system, so you can't just go in there and assign a value to it. If you do, you will get an error message as noted here. Another thing that may be useful is if you are computing new bounding box locations, for example, there are built-in functions in the Virtuoso environment that will allow you to transform, for example, a bbox. In this example, we're going to use GE transform user bbox to take an input bbox from a specific rectangle and give it a delta x and delta y as well as a rotation, and it will return to us a new set of coordinates. So in this case here, for example, we would give it a 0 colon delta y 0 for delta x would mean it would move 0 in the x direction. Delta y would be a variable with a value in it, say 5.0. It would then move it in the y direction 5.0. And then as far as the new coordinate. And then the R0 is the rotation of that box. You could supply like an R90, R180, R270, and it would then figure out the new coordinates. And then once you have the new coordinates stored in a new B box, you can do the assignment to the B box of the rectangle as shown above in the first example in the table. Now, an option to using the DB create functions that we just saw previously would be to create the shapes using what we call ROD functions. ROD refers to relative object design, and ROD was developed to enhance the ability to create layout cell views. The features of the ROD functions over the DB create functions are they can combine numerous and repetitive commands, such as creating connectivity into a single command. They provide access to parts of a shape, edges, corners, etc. without the overhead of custom skill code. They provide you the option to name objects and place them relative to one another. And this is very important because we can name instances, obviously, but allowing us to name shapes does make our code much simpler. It also makes it much easier from a hierarchical standpoint to locate data, because even though we can have an instance path down to a cell view, if we can have an instance path down to a cell view including a particular shape, that gives us a lot more power without having to do computations and lookups of that data. And the last item here is a very powerful feature of ROD, which allows us to maintain the relationships of ROD objects to one another when the objects are either edited interactively or with skill code. So the idea is you would place, say, the first ROD object at a particular point, say the first gate, and then all subsequent objects, say additional gates that are stepped off next to the original object, would be placed relative either to the original or to the adjacent object. And then when you do that, you set an align option to maintain the alignment of these shapes that were created. And that way, if any of the shapes are moved, they would all move together because they would all be they would have a permanent alignment set on them. And ROD functions are often used in P-cell development, but they are also useful in general cell development programs. So one example of using ROD is a multi-part path, and the specific multi-part path here we're going to show is a bus. So you can see in the diagram here we have a master path, which would be the one that we would specify. And then we have adjacent subpaths. And we'll see in the code, in the notes here, if you click on the notes tab, you'll see the notes that show the particular code for this. And again, we're going to specify the lower path here as the master path, and then the subsequent other paths are called offset subpaths. So if you look in the code, the main function is called ROD create path. And you give it, just like a create path function, you need to give it a layer, the points of the path, the width of the path. The justification is where the center line of the path is it center or on the edge? The cell view you're creating it in. And then to create the multi-part path, you'll see the keyword parameter offset subpath. And within the offset subpath, you have a list of lists. And each sublist is a subpath. So in the case here, the subpaths are on layer metal 1. The justification is left, which is to the left of the direction of the path. And then the sep keyword within that list indicates what the separation is between that particular subpath and the master path. So you'll see the first one in the list is the first subpath, and the separation is a variable that's been set to 1.0 called route spacing. So the separation between the center line of the first path and the second path is a route spacing value. The next subpath, the one adjacent to the first subpath, has a route spacing or a separation of route spacing times 2 plus route width. So basically, to get to the second subpath, you'll have to have 2 spacings plus the width of the first path that you place. So that distance then is indicated as route spacing times 2 plus route width. And then so on and so forth, you could add additional adjacent paths. Now, if you wanted to hard code the route spacings, that would be fine. Another alternative is to write your own function that returns this list of lists, and then in that function you would calculate each separation distance based on, say, a loop that would continue to count the route spacings and the route widths for each adjacent subpath. Another feature of ROD is to be able to create objects from other objects. So using the ROD create rect, ROD create polygon, ROD create path functions, you can create a new rectangle, polygon, or path from one or more existing ROD objects. Okay, so what happens is the existing objects are referred to as the source objects, and the new object is referred to as the generated object. So there's a keyword called fromObj that you would use to specify the source objects. So in the case below, the source object is the diffusion region, okay, the green. Then you specify the difference in size between the generated and the source objects, and to do that you would use the size keyword. And so you would basically say, my source is my diffusion, and I want to generate well, and in order to do that I want to specify an oversized value of some amount. And so if you look in the notes tab for this particular slide, what you'll see is the example code. There we have the capturing of the Cellview with GE get edit Cellview, the diffusion object we create with ROD create rect, and then the well object we also create with ROD create rect, but instead of just specifying the bounding box coordinates, we now specify the fromObj, and we refer to the diffusion object we had just created previously, and then we indicate the size, in this case 0.8, and so it will basically take that diffusion object, size it by 0.8, and create the well object. Next, we'll look at using the ROD align function to align ROD objects. And what this function will do is align a named object by a point handle on that object to a specific XY point in our design or to the point handle on a reference object. So the two key points here, there are other attributes, but one is we need to specify the align object, that is the object that will be aligned, and then the reference object, which is the object we're aligning to. And then we do that by point handles or to a particular point. We also, if we don't specify an X or a Y step, the 2 point handles would be overlapped directly on top of each other. And if we wanted an offset, we would specify an X or a Y step. And then also we would be able to specify whether or not that relationship, that alignment relationship, is either maintained when we move the objects, either with skill or interactively, or whether it's only there initially. If we only want it there initially, we set maintain to nil. If we want to keep that relationship between the objects, we would set maintain to true. If you look over at the notes slide, there's an example of aligning two objects. The first object is called small rect, and it's a ROD rectangle. The second is called big rect, also a ROD rectangle. You notice when we create it, we don't specify a location, we just specify a size. And by default then, they would both appear initially at 0, 0. Then when we call the first ROD align function, what we're going to do is take the big rect and align it to an XY point of 2.5:4. So the lower left corner would be placed at that reference point. Next, we'll align the small rectangle to the big rectangle. So we say align object to small rect. The handle is the upper left corner of the small rect. The reference object is the big rect, and the reference handle of that is the upper right. So we're taking the upper left corner of the small rect and aligning it to the upper right corner of the big rect. We did not specify any separation, so those handles will appear on top of each other when the alignment is set up. And we also did not specify to maintain it, so it will not be maintained. Here's an example of using rod align. First of all, we're going to create two rod rectangles. The first is called small rect, and it's on layer metal 1 in blue. And the second is called big rect, and it's on metal 2, which is the purple. And then in both cases, when we create them, we're going to give a width and a length. So the small one is 3 by 2 and the large one is 8 by 10. And by default, they'll both be placed at 0, 0. Now the next step, which is the crosshair icon, will be aligning the big rect, which is the one on the left there in the purple color that's on metal 2. We're going to be aligning big rect, and you can say we just use the name big rect. That's the align object. The handle is the lower left corner, and then the reference point in this case is 2.5:4. So it's going to be, x coordinate 2.5, y 4. That's going to be the lower left corner of big rect. So once that's aligned, we can now go to the next step and we can align the small rect to the big rect. So basically we're going to align the upper left corner of small rect to the upper right corner of big rect. And you can see that in the example here by the circle. So the orange circle is pointing to the location. Rod align is called. Align object is small rect. Align handle is upper left. And then the referenced object is big rect, and the reference handle is upper right. So the nice thing about this is the system maintains the handles such as lower left and upper left, upper right on all rod objects. So you don't really have to do any calculations, like you don't have to figure out what the corner is, what the vertices are of those particular shapes. You simply use the names, and so hence the name relative object design. As you're using things, handles, names, you're placing one thing relative to another. In this case, we had it exactly aligned. You could also specify spacing between them based on those handles. So again, this is a nice example of how to use rod align on shapes in your layout. Here are some related skill shape solutions you can find on the Cadence Online support site. The first one is, how do I change the layer purpose of all the shapes on a particular layer purpose pair, or LPP, using skill? So the solution here will use the database query shape tilde arrow layer name, shape tilde arrow layer purpose, along with the functions make table and LE search hierarchy to complete that task. The next one is, you can use the skill program provided here to copy all shapes of a layer from one library to another library and place those shapes on a different layer. So the solution here defines a procedure called CCS util, and again CCS stands for Cadence Customer Support, and calls various db create functions, and then it uses db save and db close to save and close the Cellviews that it opened. And the last one here is, can I create a multi-part path in skill based on a technology file template? So again, the technology file template is provided as part of the technology file, but I want to use the settings in that template in my skill program. So the solution here defines a procedure called CCS draw MPP using template, which uses the functions techGetMPPTemplate and RodCreatePath in order to accomplish that. In this next section, we want to talk about markers. Now, markers are a new database object in the Open Access database. And what it does is it indicates violations between objects in the database. It allows us to provide for different types of markers that exist for different types of violations. The area of the marker is specified by a point array. The markers are OA objects and can be used by other tools which access the database. Now, this is an important differentiation between the prior version of the database, where markers were basically placed on a layer and then properties were added to the objects on that layer that would indicate what the marker was identifying. So it was more of an informal definition. You know, some programs use like a DRCY property that explains sort of what that marker was about, but it was very much of a convention as opposed to a formal definition. So now in Open Access there's a formal definition. The markers have specific attributes that indicate, you know, what their specific purpose is. And the advantage to this is that the tools will have a consistent interpretation of the marker objects. So looking at the diagram here, we can have a figure that then references a marker. The marker is associated with Cellviews and additional figures. And the idea here of the figures, the additional figures, is that you can actually specify that the marker will not go away until the figures, for example, are removed from the design. Look in more detail at the marker delete when attribute. Now, the delete when attribute is set so that the system knows when a marker can be removed from a database. It's a string attribute. So the delete never value for this attribute would delete the marker only by explicit deletion. The delete first would delete the marker when any associated object is removed. The delete last would only delete the marker when all associated objects are removed. And finally, the delete modify would delete the object when any associated object is modified. The idea being, say for a DRC error, you're flagging, say, the spacing between two shapes as being an error. If the user goes in and, say, modifies one of the shapes, moves it, changes its shape, that's good enough for it to be removed, because obviously the user would most likely then run another DRC check on it, and if they corrected it properly, there would be no new marker generated. Next, we'll take a look at the marker severity attribute. This attribute indicates the severity of the violation shown by the marker, and it returns one of the predefined values or unsupported if the value is not valid. So the list of supported values are shown here. You can see the list here as far as acknowledged warning, annotation, critical error, fatal error, info, signed off critical error, signed off error, warning, and unsupported. The idea is here, if the marker is generated, it can be tracked to the tool. It can also have a standard message that other tools can understand, and then it can even be signed off. So in the case of an error that was reviewed by the design team but determined to be something they could sign off with, in other words, they could still produce the chip even though there was this error reported, that's also tracked here. There's also warning and unsupported. Next, we'll look at some marker skill examples. In the first example here, we'll set all the markers in a Cellview to delete never status. So here we'll capture the Cellview using the dbopen Cellview by type function, and then we'll use that to locate all of the markers with CV tilde arrow markers and then access each of the markers attribute, which is delete when with another tilde arrow delete when, and then assign to that attribute the value delete never. Next, we'll locate all of the markers with the delete, modify, and warning status. So we'll use the setOf function to filter the list of all markers, which we see here as CV tilde arrow markers. Each marker will assign to the variable called marker, and then we'll look at the delete when attribute, and when that's set to delete, modify, and we'll look at the severity attribute, and when that is set to warning. So when both of those conditions are true, then we will capture that into a list. In the last example here, we will count and create a report of all of the markers with the signed off critical error status. Next, we'll look at how to create markers using skill. The dbCreateMarker command will allow us to create a marker. The required parameters are the Cellview ID, the message, the tool, and the location, which is a list of points. Optionally, we can provide the list of objects that is associated with the marker. A visibility toggle is closed, severity, short message, and delete when. Now the first example here is an example of creating a 10 by 10 micron marker at location 00 with a message called validated. So the command here is dbCreateMarker ge get edit Cellview, which is the current Cellview we are viewing or editing. The string, which is the message that would be displayed for the user. The tool, which is important to know what tool generated this message, and then the location of that marker. In the next example here, we'll create a marker with severity equal to error and delete when equal to delete last for all the metal 2 shapes in the design. Now the marker will only be removed after all the metal 2 shapes that are associated with it have been removed from the Cellview. So this is a case where we want to establish the marker, but we do not want it to go away until the user has gone in and deleted all of the shapes that are causing that marker to have been created. So in this case, first of all, we're going to collect all of the metal 2 shapes. And we're going to say setOf shape and CV tilde arrow shapes for this particular layer name equal to metal 2. So that will filter out of all the shapes, just the metal 2 shapes. Then we'll go ahead and create the marker in the CV, and we will have the text be remove metal 2. We'll specify our tool, and then in this case we'll just again specify the coordinates of a 10 by 10 box at 00. And the additional parameters we'll provide here are the metal 2 shapes, so they will be associated with the marker. We will set T visible to T is closed to T. Then we will set the severity to error, and short message will just be empty, and finally we'll set delete last as the delete when parameter. So this is a way we would create a marker, and then once the user goes in and deletes all of the metal 2 layers associated, or all metal 2 shapes associated with this particular marker, then the marker itself would disappear. Here are several related skill marker solutions that are available to you on the Cadence Online support site. The first one is dbCreateMarker, which uses the delete when attribute, delete first, delete last, and delete modify. And so the solution provided here uses the dbCreateRect and dbCreateMarker. The next one shows you how to delete markers using skill without opening the Verify Markers Delete All form. So the skill program provided here in this solution is an alternative to the GEHI delete all marker function. And then the last example here, there's skill code provided to compare two schematics and report their discrepancies. So the solution defines a function called CCS SCH comp SCH compare, and it uses DB create marker with the delete last attribute. In the next section of this data models module, we'll be looking at hierarchy. So from a graphical standpoint, in the diagram here, you see highlighted the instance I1 of master MUX2 schematic. And if you look in the notes for this particular slide, what you would see is some different queries that we can do on the instances. The first one is just to access the list of database objects, and to do that we say MUX2 tilde arrow instances. If we want to look up a particular instance and we know the name of it, we can use the db find any inst by name function. If we want to get a list of all the master cell names, these are the cells that are referenced by the particular instances, we can use MUX2 tilde arrow instances tilde arrow cell name. Okay, the cell name attribute is the name of the master cell. Now if we just wanted the names of the instances, which would be things like I1, I2, I3, that would be referenced by the query MUX2 tilde arrow instances tilde arrow name. Here we see the Cellview and inst object types highlighted. The gray boxes indicate the current Cellview. So within the current Cellview, we can query the instances with the tilde arrow instances query and get a list of instances. If we have an inst, we can look up the Cellview. You also see the attributes clustered around the particular objects like Cellview and instance. If you want to see a list of all the master cells in the Cellview, you can say CV tilde arrow instance masters, and it will in fact point you to the master cells, which is indicated in this case by the white box with the word Cellview in it. And if the libraries are open that contain those Cellviews or instances of those Cellviews, you can then do the query from the Cellview master itself and say, give me all the inst refs. In other words, where is this Cellview master instantiated in the designs? A caveat here is if you don't have a particular design open, it will not be able to tell you where it is referenced. So some examples of the queries are listed here. We have first of all, a db open Cellview by type to obtain the MUX2 Cellview. Then we query the cell name, which is the master. And finally, we just pick an item out of the list of instances and check the cell name. And in this case, basically the nth 3, which would be actually the fourth one in the list, 0, 1, 2, 3, we grab that from MUX2 instances and we check the cell name of that, and that in fact is a NAN2. In this example called TR format instance, we have a procedure here which will print out information about a particular instance. So first of all, we pass inst into the function, then we collect the Cellview that the instance is contained in, and if we do that with the query inst tilde arrow Cellview, then we're going to just print out some information about that using a printf statement. We'll print out the name of the instance, the cell name, and then the name, the live name, cell name, and view name of the Cellview that that instance is contained in. So an important part of hierarchy in the design environment is to be able to instantiate master cells within a given Cellview. Now you can do this graphically, obviously, by just creating an instance and placing it. Within skill, what you would use is one of several commands. The first we'll talk about here is called db create inst. And to db create inst, you supply the Cellview where you will create the master in. Then you provide the master Cellview database object. Then you provide the name of the instance, the point that you'll be placing the instance at, the orientation of the instance, and then optionally you can specify the number of instances and whether it is physical only, which is related more to an inherited connections application. So the example we see here, we're creating an instance in the Cellview called in Cellview. The master is called master CV. The instance itself is going to be named inst1. The location is 0, 0. The rotation is R0. And the number of instances would be 1. Now another way to create an instance is, for example, if you're using P-cells. Now normally what you would do is you would place that P-cell in your design graphically. You would check the properties for it and you would see a list of parameters that you could modify. And you would adjust those and adjust the P-cell according to your parameter needs. And you would see that graphically appear in your environment. Now if you're doing it with skill, you would then use the db create param inst by master name. And you give it the cell view you're going to create it in. And then you give the live cell in view of the P-cell that you want to place. Then you give the name of the instance, the origin, the orientation, the number of instances, and then the differentiator between this and the prior command is you actually have highlighted here the list of parameters that you want to modify. Now if you don't provide any, it will just use the default values for those parameters. But if you do, it's a list, and it's actually a list of lists. So each sublist, as we see here, is a definition of one of the parameters. We need to give the name, the type, and the value. So you see here we specified W as the parameter name, float as the type, and 2.0 as the value. You can see the next parameter we specified is L. It's also a float, and its value is 5.0. So then when in skill, when this instance is placed, it will use the W and L that you've specified here. So we've seen that we can create hierarchy. Now we want to be able to, with skill, analyze hierarchy. In other words, there's already hierarchy in a design. We want to be able to look at that using skill. So here's two ways to look at the topology of a design. One would be more from what we'd consider more of a graphical environment, where you would see a top cell with instances A, B, and C placed in it. Then, for example, if you descended into A, you would see that A has no additional instances. If you descended into B, you would see it has C, A, and D in it. If you descended into C, you would see it also has no instances. And finally, if you descended into D, by going from top to B to D, you would see D in fact has A in it. So from a topology standpoint, designers are pretty used to using the graphical environment in that manner. Now another way to look at it, just to maybe make the programming aspect of it a little easier, is to look at the example on the right where we have more of a tree view. Okay, where top is the top cell, we have A, B, and C instantiated in it. Then looking under B, we have A, C, and D, and finally we have A. And what we're going to look at next is a traversal program that will traverse this hierarchy and find all of the master cell views in the hierarchy, not at just one level, but down through the hierarchy. So part of the job of this procedure, and it's actually a recursive procedure, is to go down the hierarchy, look at a cell, and if it has instances in it, keep going down the hierarchy. And at every time it looks at a cell, to accumulate or to keep track of that name of that cell in a list. Because, for example, let's say at top we visit A. Okay, we see A has nothing in it. That's fine. We keep track of the fact that we went into A already. Now we go into B. When we look at B, we see we have A, C, and D. Now since we've already visited A when we were at the top level, we don't have to visit A again in the B level. So in that case, we would already have that in our list, and we would not have to go into that particular cell view again. And then finally, when we get to B, we would descend into D. And again, once we hit D, we would see that we have an instance called A that we've already looked at. So the goal is to go through this hierarchy and accumulate the list of master cells in the hierarchy, and then return that. So here's the procedure we want to examine for traversing a hierarchical layout design. And what we have here again is a recursive procedure. So what you'll be able to look at here is the fact that we have a procedure called TR hierarchy traversal. And then as you look into the procedure, you will see that we actually call the same procedure again within this procedure. So we call TR hierarchy traversal in the middle of this procedure. And then what the skill environment does with a recursive procedure is it keeps track of the state of that initial call when it descends into the next call of it. And then as you return out, it retrieves the values of the prior state. So in this case, we're going to pass in the Cellview that we want to traverse, and the list so far will initially be nil, but as we go through the hierarchy, we will accumulate the names of the master cells in that list. So you can see here we have a for each loop, and for this particular Cellview that has been passed in, we're going to look at all the master cell views. We're going to set next Cellview to be the master. Then we're going to test next Cellview. Okay, and if it's nil for some reason, we're just going to return nil. The second thing we want to do is see if we've already looked at it. So we're going to use the member function to say, is this Cellview in the list so far? Okay, if it is, we just want to return no. We don't really need to go any further. And finally, if it's a valid Cellview and we haven't looked at it so far, we're going to basically descend into it and look at its master cells. So what we do is we update list so far with another call to TR hierarchy traversal. We pass in the next Cellview, the one we want to look into, and then we add next Cellview to the list so far. So for example, if we were looking at B, for example, we would then call traversal on B, but then put B in the list of things we've looked at. And then what happens is this loop continues for each instance, and we keep making calls to the traversal routine, and then it collects the master cell names. And finally, the last thing at each level it does is returns the list so far of cell views it has found. And when we finally get to the top level, that list so far will contain all of the cell views in the hierarchy. Next, we're going to look at a way that we can actually make the prior hierarchy traversal routine work for both layouts and schematics. Now, one major difference between a schematic and a layout is many times you have multiple view types that you can descend into. Where in a layout, it's always the layout cell view you're descending into. So what we see here is an option on the dbopen Cellview by type function in which we supply the library example, the cell nan2, and then we give a list of views. And what it will do is go left to right, and if, for example, the first view, Silos, exists, it will open that and return that. Second, it'll check the next one, schematic. If Silos did not exist, it will open the schematic. And then finally, if none of the views exist for a given level of hierarchy, it will just return nil. So this allows us to create essentially what's called a switch list. If you've done net listing before, switch lists are very common. And again, they specify as you're traversing the schematic hierarchy which cell views to switch into and what order. And this is how you do that with the dbopen Cellview by type command. So here's what the complete function looks like for TR switch. We basically pass in a master Cellview if it's a valid Cellview, meaning it's not nil. Then we go through the case statement. We check the Cellview type. If it's schematic symbol, we will basically then institute the dbopen Cellview by type with the switch option by supplying multiple cell views that it can switch into. Secondly, if it's not a schematic symbol, if it's just a mask layout, then we just return the master Cellview itself, assuming that that is the one we want to descend into. And if it's none of those, we would return nil. But basically it allows us to handle either a schematic or a layout properly within this hierarchy traversal. So what you'll see here is we're going to be using this TR switch up in the traversal program so that we can allow this to work for either a schematic or a layout. So here's the complete hierarchy traversal program for a schematic, and actually it works for a schematic or a layout. And so in this case, what we will do is do the exact same procedure we looked at before, but if you'll notice in the let statement, the first line in the let statement is next Cellview equals, and we used to just put master there. But now we're going to call the TR switch procedure with the master cell, and then if it's a schematic, it will switch into the appropriate cell view for that particular level. Here we'll look at using LE search hierarchy to search layout designs. There is a layout editor skill function to search the hierarchy of a layout and return the list of objects that meet specific criteria. The syntax is shown here. So the input to LE search hierarchy is a Cellview ID that you'll be searching, a bounding box which can restrict the search to a particular area of your layout, so it will look down the hierarchy within that bounding box, a stop level which will tell it how far down to look, and these two are both basically for efficiency reasons, so you're not looking necessarily at the whole hierarchy or at all levels if you don't need to. The object type of what you're looking for, and we'll see some details on that soon, and then the criteria list. What are you looking for as far as the value of that object? And then what it will do when it locates those is return to you a list of objects. Now the search is bound by the bounding box and the stop level, and the search assumes all figures are valid if the layer palette has not been initialized. So to use LE search hierarchy, we must define a criteria list, and the criteria list is basically a list of sublists, and each sublist defines a condition to test. So the example here is list cell name, that's the criteria type, operator is equal to, equal means equivalence, and then the value that we're looking for, mux2. So basically it's looking for a cell name equal to mux2. Now some of the operators here are listed. The equivalency less than equal to, greater than not equal to, exist, meaning the property exists, or not exist, the property does not exist. So that you're not testing for a value, you're just testing for existence of a property. So the different criteria types, there's a complete list in the manual, are any shape, instance, label, path, pin, polygon, and via, and you can see the variety of criteria types then that you can enter into the criteria list. Here are several LE search hierarchy examples. In the first one here, we'll look at locating vias in all 32 levels of the layout design hierarchy, matching the via named M2_M1. In the code example here, you'll see we specify the cell view, and the bounding box is the bounding box of the entire cell view, so we'll be covering the entire cell view when we specify CV_B box. We'll go through all levels when we specify 32 for the levels. We're going to look for via, and then the test that we'll do is in the list of lists here. The item in the list specifies via definition is equal to M2_M1. In the next example, we'll locate all instances and arrays of the layout design hierarchy that exactly match a specified cell name. The cell name will be stored in the variable myCell. You can see here in the code example, we're using strcat, and we're prepending to the cell name the up caret, which specifies that it must start with whatever the cell name is, and then $, meaning it must end. So no variations on it. No myCell_something or myCell something or something myCell. It just has to be exactly myCell, whatever that cell name is. So once myCell is set, we're going to do two different searches. one for instances and one for arrays. So in the first one, we specify CV as the cell view, Cellview B box, meaning the whole cell view, all 32 levels. We're looking for inst, and we're looking for the cell name equivalent to my cell. And the second one, basically the same function call, except instead of inst, we're specifying array. Now in the third example here, we'll search all of cell 2 at the top level only, so that's level 0, for paths on poly1 drawing layer with a path width greater than or equal to 3.0. So you can see in the code example here, cell 2 is passed in. We're actually giving coordinates for a particular area of cell 2. Then we specify 0, meaning we're only going to look at the top level. Then we're looking for a path. And then we have two criteria here. So we have, in the main list, we have two sublists. The first list says layer equivalent to list poly1 drawing. And the second one says path width greater than or equal to 3.0. So again, this will only look at the top level. That'll look for any path on poly1 drawing with a width greater than 3.0. So here are related skill hierarchy solutions available to you on the Cadence Online support site. First is, how can I count hierarchy depth in a given cell view? This solution uses a recursive function. The next one is delete all instances of a particular cell in a layout hierarchy. And here the solution uses the LE search hierarchy function looking for cell name. Next, how do I change via objects in my design hierarchy using skill? This again uses LE search hierarchy and looks for via definition. Next, how do you search for a user-defined property using LE search hierarchy? And again, it highlights the use of property when looking up when using LE search hierarchy. Next, how can I move the origin based on the center of a rectangle? And here we look up the layer and then are allowed to move the origin. How can I change labels from angle brackets to square brackets in the Virtuoso platform? Here the keyword we're looking for in the LE search hierarchy is text. And finally, how do I track hierarchy level while traversing a design? And in this case, the solution uses GE get inst higher and GE against higher path to keep track of the hierarchy during traversal. The next section of the data models module is to look at connectivity. Here we see NetSEL in master MUX2 schematic is highlighted within the MUX2 cell view. Some notes here is that external nets, those that go to I/O terminals, connect to a terminal with 0 or more instance terminals, typically 1. Internal nets connect 0 or more instance terminals, and those nets we'll see have a little different naming convention and do not have a terminal object associated with them. And finally, each instance terminal is on one instance. So we'll discuss in more detail what an instance terminal is. Here we see the data model diagram for term, net, and inst term object types. You can see the cell view as the main box on the left, from which you can query instances, nets, and terminals. Once you have an instance, you can then query the inst term on that particular instance, and for each inst term you can find the net associated with it. So in this case, you could build an instance-based net lister where you go through all of the instances. For each instance, you look at the inst terms and report the net it's connected to. Now the alternative way to do this is to look at all the nets. So you could say CV tilde arrow nets, get a list of all the nets in the design. Then for each net, look at the inst term that that particular net connects to. And then for each inst term that the net connects to, you could look at the instance that is connected to that inst term. So you sort of have two ways to approach the net listing challenge here. One is to do an instance-based net lister, and the other is to do a net-based one. And in the labs, in fact, you will get a chance to try both. This slide highlights the connectivity between instances and masters. So the main Cellview information is shown in the gray, and then the associated master Cellview for each instance is shown in the white box. So you can see for each instance that's placed, there is a master Cellview with associated terminals, which are in fact the inst terms when they're placed within the design. Here is some detail on figures and terminals. So again, terminals are a logical connection. To get to the physical information about those terminals, you would then say terminal tilde arrow pins, and you would get the information about the pins connected to it. Those pins, in fact, are associated with a figure, which is the physical representation of that pin and terminal. And you see, for example, a terminal is associated with a net, and the net itself can also be associated with a pin. Now, an example query might be here, for example, to determine what type of figure is associated with the terminal pins. So the query would be CV tilde arrow terminals. Then for each terminal, get the pins. Then for each pin, get the figure. And then for each figure, get the object type, which would say if it was, say, a rectangle or a polygon, for example. Here we'll look at using LE MarkNet to trace the connectivity of a net. So LE MarkNet does not use the logical connectivity in the layout design, meaning you don't need to have Virtuoso XL, Layout XL running, but instead it uses an independent algorithm to trace the net based on overlapping layers. So what it does is it marks a net in the current Cellview, meaning it traces the physical connectivity of the net in the layout design starting from the input point, and it highlights the trace net or nets. So the syntax here, LE MarkNet takes as input a point, that would be the starting point where it would start to look for the net under that point. And then there's some keyword parameters. You can specify start level, stop level, highlight incrementally, say vinfo, thick line, and then you can even provide an option file for MarkNet with some additional options. So in the example here, we have LE MarkNet. We're giving it a list of 2 points, 5.7, 9.0, that's the starting point. We're going to ask it to start at level 0 and stop at level 32. And the MarkNet color it'll use is a system layer. If you look it up, it's be Y2 drawing. So whatever color Y2 is, it'll mark the net with that color on the layout design. Here are some related skill connectivity solutions that you can find on the Cadence Online support site. The first one is how can I change pin name, pin label, and net name. So this solution defines a function called CCS change label and CCS change pin. The next one, how do I make MarkNet use a specific layer Y4 drawing to trace the net? So in the solution, you'll see the CCS MarkNet function defined and the CCS traceNet. Both of those will use the LE MarkNet function. Next, how do I set defaults for MarkNet via layers, connected layers, and stop layers? So the solution here outlines how to use the MarkNet options file for that purpose. And finally, how can I make MarkNet work with 2 poly layers and local interconnect or LI layers? So the solution here identifies where to specify the steps to define the text file layers. The next section of the data model module covers vias. So in IC 6.1, all vias are defined in the technology file. Vias are database objects, and unlike in the prior version of the database in the 5.1 environment, they are not instances. Standard vias have all details described in the text file. So in this case, you can see the standard via def's definition section in the text file. First via defined is called via 01. It's between poly and metal 1 and uses the contact layer. The second via is called via 12. It's between metal 1 and metal 2 and uses the via 1 layer. Now custom vias have a p-cell or fixed Cellview associated with them, but they are also defined in the text file, and you can see here we have several examples in the custom via defs section. They have a name and then they refer to a lib, a cell, and a view. Now the advantage of using standard vias is that the tools will be able to better optimize the layout because they know all of the underlying dimensions that can be modified, for example, to make a via array at an intersection of two layers. Here's a quick comparison of standard and custom vias. So standard vias can be the source of a wide variety of via placement topologies. Tools can place optimum arrays of vias, for example, because of the relationship of the layers and the rules is completely defined. Custom vias are often fixed devices. The layers and rules for the via cannot be known by the application placing the vias, so making optimum via placements is usually not possible. Now for each unique via variant, there's a unique custom via def that must be entered into the text file, so there's also the overhead of maintaining the set of custom vias as opposed to using the standard vias. So when we locate vias and via parameters, we'll see that there's basically two parts to it. The one is the information in the database, and the other is the information in the text file. So you can see that shown here, that if you look at a via and you look at the via header, it will then point to the text file definition called a via def. And then associated with the via header for the particular via that's placed in your design are what's called override params. And these would be the params that were set to override the default params that are in the text file definition to the right. And so after the technology file is loaded or attached, it becomes part of the database and the vias are then accessible. Now here's an example of printing out all vias and their locations and parameters. So first of all, we get a Cellview, and then for each via in CV tilde arrow vias, so that's our query to collect all of the via database objects, we're going to print out some information first about the via, the location, and then the name. And then what we're going to do is go through for that particular via the list of the parameters. And this would be the override param. So we're going to say for each param list, basically located by via header override params, print out that list. And that would be a list of the parameter overrides that would be exist for that particular via instance as opposed to the default parameters. Here we'll look at creating vias with the db create via function. You can see the syntax here. First of all, we pass in the Cellview ID where we will be creating the via. Then we pass in the via def ID, and we'll explain how to get that. And then a point and an orientation where we want it placed. And finally, a parameter list if we want to override any of the default parameters. So first of all, we'll need to look up the via def ID, and we'll do that by locating the via in the text file. We'll see an example on the next slide where we'll show you more details on how to do that. But basically, we need that via def ID. We'll use a function to get that. And then we'll also need to know the name of the parameter in the text file. And so to locate that, you can basically dump the text file and take a look. There's a nice utility called the text file manager, technology file manager.
So you select CIW Tools, Technology File Manager, Dump, and then you'll select the technology file where the vias are located. Select via defs, that's what you want to dump. Then the ASCII file that you'll be dumping the text data into. Click Open in Text File IDE, and it will open the ASCII file in the text file IDE viewer editor, which makes it a little easier to find information. And then just click OK. And you can see in the graphics on the right there, the dump technology file form is shown with the settings. And then when you click OK or apply, it will launch the text file IDE. And finally, you can see in the text file IDE that there's information stored for the standard vias. The names are listed there: cut layer, cut width, cut height, etc. If it's a custom via, then it'll just have a property name, property type, value for a custom via. But for the standard ones, they're listed there in the text file. And so that's basically how you approach the db create via command. You have to get the via def ID and then also provide any override parameters. Here's an example of creating vias. So the code is shown here on the left with a diagram of two vias that are being placed. One is a standard via with the default parameters, that's V1. And the second one on the right is V2, and that has an override parameter where we're overriding the cut width parameter with a value of 2. So you can see in the code here, the first thing we need to do on the left there is get the text file ID. And that's basically get text file, calling ddgetObject on the library containing the vias, which is in this case CellTechLib. Next, we want to use the function techFindViaDef by name, pass in the text file ID, and then the name of the via. And again, the name of the via we'll get by looking it up. We mentioned on the prior slide that you can launch it through the Technology File Manager dump option and take a look in the text file to find the actual name. In this case, it's M2_M1. We also are going to need the Cellview ID of the current Cellview because we're going to be creating it there. We could use some other function to get another Cellview, but we're going to just use the current one. And then the first thing we're going to do with V1 is we're going to call dbCreateVia, give it the Cellview, the ID, the via ID, the location, in this case 00, and then the rotation, which is R0. And then if we take a look, we can query, we look at via1, via header, override params, and it's no, there are none. There's no override params. Now in the second case, we'll be placing a via with a new parameter value, that's an override. So in this case, we have v2 is going to be the same command as v1, basically dbCreateVia. We're putting at a new location, x is 10, y is 0, and we're going to specify the cut width of 2. So we're going to override it, and you'll see that the width of the via graphically is actually wider. And then if we do a query on that, v2 tilde arrow via header tilde arrow override params, we do see that the cut width is now 2.0. So we have two examples here, one with just using the standard parameters, one with using override parameters.
Here are some related skill via solutions that can be found on the Cadence Online support site. In the first one, how do I change via objects in my design hierarchically using the skill language? So there is a function defined in this solution called CCS replace via, and it uses techGetTextFile, LESearch hierarchy, and LEReplace to accomplish that. In the next one, how do I get the via ID from the text file and create a via in P-Cell skill code? So support of the nil argument for the text file default parameters in 616 is specified. So what you'll do is look at the solution here. It uses techFindViaDef by name to locate the via, and then it uses dbCreateVia, and then shows how to override the parameters on that via and the next one, how do I calculate parameters for dbCreate via that are correct by design rules and constraints? So in the solution here, it'll use the command dbCreate via, lxGetValid via defs, and lxCompute via param functions. The lx prefix commands require the Virtuoso Layout Suite XL license. Next, we want to talk about properties, and every database object is a kind of generic database object. So when we say properties, we mean properties that you can add to any database object. Now, each specific database object that we've talked about has an object type. It has a cell view it's associated with, and it also has a prop attribute. And this prop attribute is what contains the information about the properties that you would add to the particular object. So here in this data model diagram, you can see the generic database object is the ellipse. We then see that if we say whatever database object we have, tilde arrow prop, we'll get a list of the properties. Those properties will have a name, a value, and a value type. And that we see that generic database object, whatever it is, a net, a Cellview, a net, a Cellview, a instance, a via, will basically be associated with a Cellview. So what are user-defined properties? The applications that you create are responsible for creating, updating, and interpreting the user-defined properties. Now, CDBA and Open Access represent a user-defined property by a database object with an object type prop. Every database object except prop objects themselves can have 0 or more user-defined properties. And the database stores all the properties on an object as the value of the prop attribute. So here's an example. We'll assume that Windows 5 is displaying the Cellview master MUX2 schematic and that it has some properties on it. So first of all, we'll get the Cellview with the GE-get Windows Cellview function. Then we'll query the prop on that particular Cellview, which is the list of properties, CV tilde arrow prop. And then we'll look at the object types of those properties, which they're all going to be prop object types. But that way you can quickly see for any object with this simple query CV tilde arrow prop if any properties are stored there. Here we'll look at some queries to examine user-defined properties. The first is just tilde arrow prop. That gets the list of all properties. The next is tilde arrow prop tilde arrow name, which gets you the names. And then we have tilde arrow prop tilde arrow value, which retrieves the list of the property values. So here you can see some examples looking up the name, looking up the value, and looking up the value type. If you have a unique name, like net pound, for example, you can put that in double quotes. And if you happen to know the name of the property, like net pound, you can look it up on a particular object. You can just say db find prop CV, look for the string net pound, and then check the value type in this case. But this is an easy way to locate and extract properties. Next, we'll look at how we create user-defined properties using skill. It's very straightforward. We just use the tilde arrow operator, and then we give a name of a property that we make up for our particular application, and then we store a value there. So we say in the first case, CV tilde arrow tr string prop equals the string hi. We'll see it automatically set the value type for us. Next, we make tr float prop and assign it a value and place it onto the Cellview. And then finally, we add another property onto the Cellview called tril list prop and make it a list. So we're just showing here that it's very easy to create a property and create it of any type. Now, in order to create specific types like a time property, for example, you would look up in the skill finder functions that start with dbCreate .prop, and this would allow you to locate additional property creation functions for things other than the standard types, and again, such as time. Now, enumerated could be a list of particular values that you might want to have, like maybe you only want the user to be able to put like R0, R90, R270. And a range would be just a range of numbers. Maybe if you're asking for a percentage as input, you would just have the range be 0 to 100. And finally, you can also create hierarchical user-defined properties, and we'll look at that on the next slide. So next we'll look at the hierarchical user-defined properties. They basically allow you to create a small data structure that is placed on the object that will store properties. The function is called dbCreateHierProp. And then what you will do once you create that is add additional properties into the HierProp object associated with the Cellview. So here the first thing we do is we do a dbCreateHierProp on the object, which in this case is a Cellview called trHierProp. And we assign that to the variable HP, short for hierarchical prop, and then we just say HP tilde arrow A equals 1, HP tilde arrow B equals 2. And then we've essentially created on that Cellview a hierarchical prop named HP, and under it stored additional values. And you can see we query it just like we would a standard property, but this is in fact a hierarchical property. So as you likely recall, to retrieve all attributes of a database object, you can use tilde arrow question mark and return to you the list of all the attribute names on that particular database object. And you can use tilde arrow double question mark, and that will return the list of the attribute names and their values. And in the next slide, we'll look at basically a utility that will allow you to do that more quickly and efficiently using a graphical display. In order to look at attributes on a database object, you can use the skill functions we've mentioned previously. With this course, we're also providing a utility called TR-Data-Browser. And this utility will display the attribute names and values for a database object in a tree graph window. So the added value of this utility is the graphical interface. In the data browser, you can perform the following tasks. You can browse any displayed database objects. You can expand an object in the tree to see the attributes and values. You can compact or unexpand the tree. And you can select any object in the tree graph window and open it in its own new window as the root of its own tree. So this helps when you're trying to manage the size of the information you're seeing in a particular window, or the amount of information. And then you can also use the right mouse button to access these commands. So the value of this is it's faster to view database object and attributes versus typing the query commands in the CIW. Now the TR Data Browser is not part of the standard Cadence software. It's only available as part of this course. So in order to use the TR Data Browser utility, first of all you'll want to open up a Cellview window. Next you will load the trdatabrowser.il function as provided in the lab database. And then finally you'll launch the TR Data Browser by entering TR Data Browser // in the CIW, and it will use the Cellview that you have opened as the root of the browser. And you can see a little example of the interface on the right here. Mux2 layout is the root, that's the Cellview, and from there we're able to query, in this case, instances, and we can in fact open the instances into its own new browser by right-clicking and saying expand to new browser. So you can kind of see a little bit of the interface in the lab. You'll get to try it. So in summary, we reviewed the major database object concepts. We opened a Cellview non-graphically into virtual memory. We created shapes in a design. We also, using both standard dbCreate functions and ROD functions, We looked at the Cellview database model from a geometry, hierarchy, connectivity, and property standpoint. We examined how to traverse a hierarchical database. And then we also looked at an application for retrieving and viewing all attributes on a specific database object. And